Today's lesson, we're going to look at electrical conductivity and hardness and see how the different types of bonding influence these two properties. So firstly, electrical conductivity. So the electrical conductivity of different types of substances can be explained by looking at the bonding structure and electron configuration of those substances. So the electrical conductivity can be described if we simply consider the bonding structure. Now, often by studying the properties of a substance, information about the bonding structure can be inferred. You could go one of two ways. You could say, look, we have this property, we can explain that property because of the bonding structure. Or if you had a new material that you didn't know anything about, you could use electrical conductivity to see or to learn something about the way that its bonding structure is. So for instance, if I knew it conducted electricity very well, then I would likely think that it would be a metal. Or if it didn't conduct electricity well, it could be any of the other three. And if it could conduct in solution, then maybe it would be an ionic substance. So you can see by looking at the properties, we can actually infer something about the way it's bonded. So that's what we're trying to do in today's lesson. So ionic substances. Ionic substances cannot conduct in solid state, but can conduct in liquid and aqueous states. This is for electrical conductivity, which we're studying. Okay, so since all the electrons are bound in a particular ion, and each of the ions is stationary, there are no free charges to conduct electricity. So you can see here, in the solid state, because they're so tightly bound together, each of the ions is actually stuck. They're trying to move to the right direction, but they're just being held so tightly that they can't get in the right place. They can't actually separate and move to where they want to be. So you'd see the positive ones would try to move to the negative terminal, and the negative ones would try to move to the positive terminal. But because they're so tightly bound, they can't actually move, so they can't conduct electricity because there's no flow of charge. In the other case, when it's molten or aqueous, the charges in the ion form are more mobile, and so they can allow the substance to conduct electricity because they can move really consistent way. So you can see here, now they're all scattered in a liquid state or aqueous state. When the charge is applied, they can actually drift to each terminal. So the positive charges move to the left because of the negative terminal, and the negative charges move to the right because of this positive terminal here. You can see they all kind of drift, and that is actually what we call current, because it's charges moving in one direction. That's why ionic substances can conduct in molten or aqueous state rather than in solid state. But what about covalent substances? Both covalent network and covalent molecular substances don't conduct. Because the electrons are tied up in the covalent bond, they're not free to move, and thus the substance doesn't conduct electricity. Because they're locked up in those covalent bonds, they can't actually separate. There's no ions because they're sharing the electrons, so everything's electrically neutral. There's no movement of charge at all, so you can't have any electrical conductivity. The molecules and networks are generally electrically neutral, so in liquid state, there is still no conduction as there are no free charges. So even in the liquid state, there are no free charges because everything's electrically neutral, so you can't even have electrical conductivity in liquid state. Metallic bonds? Obviously, metallic bonds conduct electricity very well, otherwise we wouldn't use metals in our wires. And the reason is because of the large number of delocalized electrons, which are free to move throughout the lattice of the metal. The abundance of free charges allows for a high conductivity. So now that we've covered electrical conductivity, we're going to move to another property, and it's going to be hardness. So hardness is the measure of an object's resistance to deformation. What does that mean? But you know intrinsically, sort of intuitively, what soft and hard mean. For instance, if I had something soft, I could apply very little force, and I could get it to deform or change shape and stay that way. For instance, let's take Play-Doh. If I, for instance, bent Play-Doh in half, I could bend it and it would stay that way. But I can't do the same thing with steel. I'm not strong enough to bend steel and make it stay that way. Obviously, steel is harder than Play-Doh. Even harder to do than that is crystal substances. So steel will bend eventually if I apply enough force, but crystals will just shatter. So they're much harder, but also more brittle. So that's what I mean by deformation. I can change the shape and have it stay that way. Now, this property is useful for describing the forces holding onto individual units of a substance. So it's useful for describing how strong is the force holding each unit within the entire structure. Very hard substances often have very strong bonds holding each unit of a substance to the adjacent units. So if it's a covalent network substance, each unit is the atom, which is bonded to 4 adjacent atoms or more, whichever one. And in an ionic substance, it's the positive and negative charge, and that's the unit that we're talking about. If you have a very hard substance, each of the units is being held to adjacent units very, very strongly. So in ionic compounds in general are all very hard. Now this is because there's very strong electrostatic forces holding the ions together, so they don't want to move around next to each other. Any attempt to move the ions will incur stiff resistance, as ions hold one another in place. In order to deform something, I need to be able to move its molecules or its particles from place to place. And because the ionic substances are so strongly held together to one another, they don't want ions moving from place to place. So they'll resist me trying to deform it. And that's why they're very hard. If too much energy is supplied to shift the ions, the crystal will likely just shatter rather than deform. So that's what makes ionic substances a bit different. Covalent network, essentially the same as ionic compounds. They're very, very hard because they're bonded very, very strongly together. But instead of electrostatic forces holding the ions together, we've got covalent bonds binding the atoms together. Okay, so there's the subtle difference between a covalent network and ionic substance. Again, oversupply of energy will still cause shattering. So it'll still shatter if you put too much energy in. But you can see they're very similar to ionic compounds. The only difference being covalent bonds rather than ionic bonds and atoms rather than ions. And we've got covalent molecular substances now. These substances are often not hard at all. There's no hardness in covalent molecular substances. This is because the forces holding the particles in the substance are extremely weak. Individual molecules are held together with very weak forces. And these weak forces don't resist the deformation. They end up just taking the shape of whatever container they're in. So they don't resist deformation very well. So this results in an extremely soft substance that can have its shape change very easily. So with covalent molecular substances, the shape can be altered very easily, but maybe not permanently because a lot of them are gases. So metallic bonds. In between covalent molecular and ionic covalent network substances is metallic bonds. They sit in between covalent molecular, ionic or covalent network substances in terms of their malleability or their hardness. So while these two are very, very hard, and this one's extremely soft, metals are somewhere in between. With the application of force, metals can be deformed. However, they don't really shatter. You don't really see a metal shattering unless you freeze it. But at normal temperatures, if you were to hit a metal, it doesn't just explode into a million pieces. It tends to just change shape. This is because of the flexibility of the metallic bond. It's just flexible. The bond is actually a lot more flexible than ionic or covalent network, and that's why it can be altered very easily. Now, since there is no set place that the electrons have to be, changes in the lattice are easy to make. So, for instance, this is our substance. The electrons don't have to be anywhere in particular. So if for some reason that these ions get shifted over, then the electrons just travel this way or this way, rather than where they were before. That's essentially what's going on. So once the lattice changes, the electrons will simply move in a different way than they did before. And so that's why they can still stay in the lattice, but the lattice can actually change shape, simply because the electrons don't have to be in the same place at any one time. Okay? So that concludes today's lesson on electrical conductivity and hardness. We looked at these two properties and sort of explained them based on what we know about the different bonding types. So we'll move on to the question segment now, and hopefully you'll be able to develop more of an understanding about the four bonding types: electrical conductivity and hardness.